Okay, now let's move on further. This is the thing we discussed last week, but the only difference is that we provided the values as being 1, x of n minus x of n minus 1. We have discussed that this was actually the high pass filter, right? So we'll start with this. Like no, this one represent, this is the first order difference expression. Even this sign is plus or minus, it doesn't matter. Once we have the frequency response, we get to know how they are actually plotted. So we had done these things previously in the, so I'm just kind of going through them quickly. We did this and we end up in an expression like this. See, we had this expression, and then we actually, remember this was the phase and this was the amplitude, and then we plotted it. Now you remember the plot was like this. That was for the high pass filter, right? And then in case this sign become plus, so it become the low pass filter, and this become the response. Similarly, the corresponding response for this one was, this was the phase response, and the blue one is for the high pass. If you remember, we did that in the class last week. I have to add this because actually section B missed out the class, so this particular portion is for them. So this is the first order relationship. You transform it into impulse response expression. You take this frequency response, you rearrange the expression into the format that you can plot. You end up with an amplitude, and you end up with a phase. And then these are the graphs that you end up with. Okay, next is cascading. You can have multiple filters one after another. This is the beauty of digital systems. They are kind of commutative, so you can have one system before another, because all the systems, if you have 10 systems, they are actually internally convolved with each other. So the final expression of the filter is going to be h of, let's say the first one is h of 1, the second one is h2, third one is h3. So the final is going to be h1 convolution h2 convolution h3. So you can have all of them in the cascaded form, and ultimately they keep on adding to each other. So if you want a 5th order filter or 6th order filter, you can create it from 3 second order filter, or you can create it from 2 3 order filter, or you can create it from 6 first order filter. Okay, so yeah, this is, if you look at it, this look like a running sum. No, this is, if you take the average, it become the running or moving average. If you don't take the average, it is, sometimes you will listen to the word called moving or running sum filter. So this is an example of running sum filter, where you have 5 points, x of n minus 1, x of n minus 2, x of n minus 3, and x of n minus 4. This is a 4th order filter, but currently we don't know whether it is high pass, low pass. So this is also another assignment for you guys, to find out its impulse response and plot it. Now this is the kind of thing that you have to do it manually, and we can discuss later on in the MATLAB course how to do it using the MATLAB code. But you have to perform this arithmetics. You have to find out h of n. So you will end up having an expression for h of n, and then you have to plot it. You will end up in an expression that is usually termed as Dirichlet function. So that is hint for you what kind of graph you're gonna end up with. Okay, so also see, like I discussed earlier on, running sum, moving average, or running average filter can be converted into low pass, high pass, band pass. So we can discuss that at a later stage, how to do that. But currently you have to find out whether this, based on this expression, whether it is a low pass or high pass filter at this stage, right? Okay, we had discussion about this a little earlier on. Okay, you do remember this thing, that y of n for any expression in finite impulse response system is actually x of n convolution h of n, which end up with an expression like this, right? Where m shows the number of points in the system. Okay, these are the things that you have previously actually been through in signaling system. I'm just adding these slides just to give you an overview and how to go through it. Okay, now let's see why we have to do these filtering, why it's important. Filtering previously in different courses, the idea was to remove noise or something. But in case of digital signal processing, it's mostly about getting the desired result from a system. No, it's not necessary that the rest of the things are nice, or it can be something else. It doesn't matter. From a same kind of input data, you might be interested to get multiple outputs. So then you might need multiple different types of filter. So you can't term the rest of the data as being nice. But the general concept is everything that you don't want is usually considered as nice. And we say that as being actually added to the system, and we have to remove to get the original actual system output. Ideal filter is supposed to give you exactly the same desired output from the system with a little bit delay. Now, like this is what we discussed earlier on, that if in a digital system, the problem is that if you pass any signal through it, the number of samples in the output are usually more than the number of samples in the input. And that's not actually a good thing. The general thing is that it can be delayed. Why it should be delayed? Because the system is going to take some time to process the signal. So that delay is there. That's fine. That's absolutely fine. But having more samples, that naturally means there is some noise that is added to it, which we're going to discuss at a later stage. Okay, so one more thing. You have to keep one thing in mind. See, the ideal filter response is supposed to be sharpened like this. And it should have a linear phase. What do we mean by linear phase? Why linear phase is important? Linear phase is important in a sense that if I pass multiple signal frequencies to the system, they should be delayed linearly with respect to frequency. Because if it's high frequency and low frequency, based on the frequency, it should be delayed by that amount so that it is linearly distributed across them. Otherwise, the shape of the output signal is going to be different. And we all know that the information is always stored in the shape of the signal. It's not in the values. The variation is important. So the ideal response is supposed to look like this, and the ideal phase response is supposed to be linear always. So you have to look for these two things in any filter. Now the problem is that we want that the system to be causal. That means it cannot have samples before 0, right? That means the system actually start from 0. So for a system to be causal, it should be only dependent on the previous value. If that's the case, what's going to happen is that we can never have ideal response. We can never have the passband to be 0. That means there is going to be always some values out here. There's always going to be some values in here. So we can never get this kind of response. This is the reason the response that we get are actually completely different than we actually expect, even in the digital systems. So according to Pele and Wiener theorem, we can never get ideal response from any causal system. By causal, we mean the real system, the system that actually depends on the past and present value, not on the future value. So this is the reason, instead of this, we always end up with this. It's the only thing we do is that we keep on reducing these ripples. This is our target. We keep on reducing these ripples, which is our target, and we keep on making it sharp. You know, we were talking about the order of the filter. No, the order of the filter actually define how sharp it is going to be, right? The ripples are actually a different factor, but the sharpness is defined by the order of the filter. The higher order you have, the more sharper you're going to have this response. And see, this is like ideally supposed to be slightly down to 0. Now, okay, what are the advantages and what are the disadvantages of the FIR filter? They have to be non-recursive. That means they don't have a feedback system. They are always depending on only the input signal. It's not the system output. If there is no feedback in it, one.